Today, we will talk about the properties of exponents. This is an exponent. It is read as 2 to the 5th power, or 2 to the power of 5. The big number, 2, is our base, and the little number at the top, or the superscript, 5, is our exponent. This number, 2 to the power of 5, is written in exponential form. Now, let's try expanding our number in exponential form. To do this, we will need to know what the base and the exponent are. The base is the number you multiply. The exponent is the number of times you write the base. In this case, you would write the number 2 5 times, and you would put a multiplication sign between each pair of 2's. So, 2 to the 5th in expanded form is 2 times 2 times 2 times 2 times 2. If we multiply all of these together, we will get the number in standard form. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So 2 to the 5th power is 32. Now, let's consider a generic example, x to the 3rd. The exponent 3 tells us that we must write the base x 3 times. Make sure you put a multiplication sign between each pair of x's. So x to the 3rd is x times x times x when expanded. Let's look at another example, x squared. The exponent 2 tells us we must write the base x 2 times. When we add our multiplication sign, we get x squared is x times x when expanded. Now, we will look at some properties of exponents. The first property is the product rule. To investigate this, we are going to use the example of x squared times x to the 3rd. As we figured out a minute ago, x squared is x times x, and x third is x times x times x. So, if we write this out, we see that we actually have 1, 2, 3, 4, 5 x's. So x to the 2nd times x to the 3rd is x to the 5th. Let's have a look for a second. What did we actually do to the 2 and the 3 to get a 5? Well, 2 plus 3 is 5, so we added. We need to figure out if this is always true. If when we are multiplying two numbers with the same base but different exponents, we can add the exponents and leave the base the same. If this is true for every pair of exponents that you multiply together, then x to the a times x to the b will give you x to the a plus b. This form, where we replace both our base and our exponent with generic letters or variables, is called a rule. Let's investigate this rule further. Let's look at y to the 5th times y to the 4th. Y to the 5th is y times y times y times y times y. Now we're going to times that by y to the 4th, which is y times y times y times y. We will get a total of 9 y's. So y to the 5th times y to the 4th is y to the 9th. And if we try our rule, then y to the 5th times y to the 4th will give us y to the 5 plus 4, which is y to the 9. This rule does hold up. That means that if we have something like x to the 15th power times x to the power of 21, we can figure out what the exponent is. By adding 15 plus 21, we get x to the 36th power. Let's consider a numeric example. In this case, let's do 3 squared times 3 to the 3rd. If this rule holds up, then 3 squared times 3 to the 3rd will give us 3 to the 5th. So first, let's figure out what 3 to the 5th is. Well, 3 times 3 is 9, times 3 is 27, times 3 is 81, times 3 is 243. Now, let's try these numbers individually. 3 squared is 9, and 3 to the third power is 27. 9 times 27 does in fact give us 243. Let's look at one last example. What happens when we have different bases? Let's try this with x squared times y to the third. Well, x squared is x times x, and y to the third is y times y times y. When we look at this, we can't really combine anything. Nothing says that x and y are the same. So that means we still have 2 x's and 3 y's, so x squared times y to the third is just x squared times y to the third. We can't do anything to it. Next, we will consider the quotient rule. What happens when you take an exponent and divide by another exponent with the same base? Well, let's try this with x to the third divided by x squared. Remember, a division sign can be written as a fraction. So we have x to the third over x to the second, which if we expand this out, we get 3 x's on the top and 2 x's on the bottom. Do you remember how whenever you have a number and you divide by itself, you always get 1? So the same thing happens with variables. X divided by x is just 1. This pair cancels out. This pair also cancels out, and we are left with 1x, or x to the first power. Now, what did we do to the exponents to get our new exponent? Well, 3 minus 2 is 1, so we subtracted. Hey, this kind of makes sense because our product rule, when we multiplied, we had to add the exponents. For our quotient rule, when we divide, which is the opposite of multiplication, we have to subtract our exponents, which is the opposite of addition. So, to find the quotient of two exponents with the same base, we subtract the exponent. If this is true, then our rule will be x to the a divided by x to the b will give you x to the a minus b. Let's check this out to make sure it's true. If we take x to the 7th times y to the 5th over the whole quantity x to the 3rd times y to the 2nd, we will get 7 x's on the top and 5 y's on the top. We will get 3 x's on the bottom and 2 y's on the bottom. Then we can simplify this by getting rid of the pairs of x's and the pairs of y's, and that leaves us with x to the 4th times y to the 3rd. Does this follow our rule? Well, x to the 7th divided by x to the 3rd will give you x to the 7 minus 3, which is x to the 4th. And y to the 5th divided by y to the 2nd will give you y to the 5 minus 2, which is y to the 3rd. This checks out. That means that if we have something like x to the 1000 divided by x to the 250, all we need to do is subtract our exponents. So x to the 1000 minus 250 is x to the 750. Now, what happens when we try this with numbers? Well, let's consider 5 to the 3rd over 5 to the 2nd. If we do this the traditional way, then 5 to the 3rd is 125 divided by 5 to the 2nd, which is 25. And 125 divided by 25 is 5. If we do this the rule way, then 5 to the 3rd divided by 5 to the 2nd is 5 to the 3 over 2, which is 5 to the 1st, or just 5. Since you get the same answer either way, we can show that the rule does work. Now we're going to look at the power rule, or what happens when you raise an exponent to a power. Let's look at the example x to the 3rd to the 2nd power. In this case, the power of 2 tells us that we need to write the whole quantity x to the third twice and multiply it by itself. So if we were to write this x to the third out, we would have x times x times x. And if we write the second x to the third out, we have x times x again, for a total of x to the sixth. Now what did we do to the exponents 3 and 2 to get 6? Well, we multiplied. So right now, our theory is that when you raise a power to a power, you have to multiply the exponents. That means that x to the a, the whole quantity raised to the power of b, will give you x to the a times b. Let's try this with another example. Y to the fourth raised to the third power. Well, the exponent 3 tells us we need to write the whole quantity in parentheses, y to the fourth, 3 times. So y to the fourth times y to the fourth times y to the fourth. Y to the fourth is just y times y times y times y. So if we do this 3 times, we will then be able to count our y's, and we get 12 y's, also known as y to the power of 12. So does this match our rule? Well, y to the fourth to the third power should be y to the 4 times 3, which is y to the 12th. Our rule does check out. If we wanted to try this with numbers, we might say 3 to the second raised to the 4th power. So 3 to the second power is 9 raised to the 4th power is 6,561. If we were to use the rule, then we would say 3 to the 2 times 4, which is 3 to the 8th power, which is also 6,561. So it does not matter which way we do this, we still get the same answer. The rule checks out. Now, if we were to try a random problem, let's say x to the 15th raised to the 5th power, we could figure out what the exponent was by multiplying the power by the power. So it would be x to the 15 times 5. And 15 times 5 is 75. So we could write it as x to the 75th power using our rule. Next, we will look at the power of a product. Let's look at the example x to the 7th times y to the 5th, the whole quantity raised to the third power. Well, x to the 7, y to the 5th will be written 3 times, all multiplied by each other. And then we can actually rearrange these so that all the x's are next to each other and all the y's are next to each other. So x to the 7th, x to the 7th, x to the 7th times y to the 5th times y to the 5th times y to the 5th. In this case, if we do the products, then x to the 7th times x to the 7th times x to the 7th will be x to the 7 plus 7 plus 7, which is x to the 21. And y to the 5th, y to the 5th, y to the 5th will be y to the 5 plus 5 plus 5, which is y to the 15th. Therefore, whenever we do a power of a product, we can do the power of the individual factors or exponents. This would be, in parentheses, x to the a, y to the b, all raised to the power c, gives us x to the a times c times y to the b times c. If we wanted to do this with numbers, then we would do 2 squared times 3 to the first, all raised to the third power, gives us 2 to the 6th times 3 to the third. 2 to the 6th is 64, and 3 to the third is 27. When you multiply those together, you get 1,728. If we were to do this the traditional way, then 2 raised to the second power would be 4 and 3 to the first power would be 3. 4 times 3 is 12 to the third power is 1,728. So this rule does check out. So let's try using the rule on some bigger numbers. X to the 500 times y to the 25th, all raised to the 5th power. This should give us x to the 500 times 5, y to the 25 times 5, which is x to the 2500th power and y to the 125th power. Once again, we got this by using our exponent rule up top. Next, let's consider the power of a quotient. So what happens when you take a quantity, let's say x divided by y, and raise it to the 5th power? Well, that means that we're going to have 5x over y's multiplied together. Remember when we did fraction multiplication, we said we just multiply across. So x times x times x times x times x is x to the 5th. And y times y times y times y times y is y to the 5th. To do the power of a quotient, we took the numerator and raised it to the power of the exponent, and then we took the denominator and raised it to the power of the exponent. If we were to write this out as a rule, then it would be in parentheses the quotient x over y, all raised to the a power gives us the numerator x to the a over the denominator y to the a. Let's look at another example. X to the third divided by y to the second, all raised to the 4th power. Well, that means we have to have 4 of the quantity x to the third over y to the second multiplied together. When we multiply across and use our product rule, we get x to the third times x to the third times x to the third times x to the third, which is x to the 3 plus 3 plus 3 plus 3, or x to the 12th. On the bottom, we get y to the second times y to the second times y to the second times y to the second, or y to the 2 plus 2 plus 2 plus 2, which is y to the 8th power. Now, does this rule check out? X to the third over y to the second raised to the 4th power would give us x to the 3 times 4, which is x to the 12th, over y to the 2 times 4, which is y to the 8th. The rule does work. Now, let's look at an example with a number. Let's do 1/3 to the 4th power. So if we were to do this normally, we would have to say 1/3 times 1/3 times 1/3 times 1/3 is 1 over 81. If we did it with the rule, then we would say 1 over 3 to the 4th power is 1 to the 4th over 3 to the 4th. 1 to the 4th power is 1, and 3 to the 4th power is 81. Since we get the same thing both times, this does check out. Now, let's try a really big number. For example, let's use the quantity x to the 5th divided by y to the 4th, all raised to the 100th power. So what we would have then is x to the 5 times 100 over y to the 4 times 100, which would give us x to the 500th power over y to the 400th power. So that's how we use the rule for the power of a quotient. Now, let's look at what happens when we have a negative exponent. So let's consider the quantity x squared divided by x to the 8th power. If we were to expand this out, we would have x times x over x times 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 x. After canceling these out, what we would have is nothing on the top, and that means we're just going to use 1 because any number divided by itself is 1. And then on the bottom, we actually have 6 x's, so x to the 6th. So the whole quantity is 1 over x to the 6th. If we were to write this using the quotient rule, then it would be x to the 2 minus 8, which is x to the negative 6. That means that whenever you have a negative exponent, you can write your base as its reciprocal, and the exponent is now positive. In terms of rules, this would be x to the negative a equals 1 over x to the a. Let's try this with another example to make sure it works. X to the third power times y to the second power all over the quantity x to the fifth times y to the fourth. If we were to write this out, we would have 3x's on the top and 5x's on the bottom. When the pairs are canceled out, we are left with x squared in the denominator. We also have 2 y's on the top and 4 on the bottom. When the pairs of y's are canceled out, we're left with 2 y's on the bottom, so y squared. This means that our final answer would be 1 over x to the second y to the second. Now, let's see what happens when we use the rule. X to the 3 minus 5 times y to the 2 minus 4 gives us x to the minus 2 and y to the minus 2. That does check out. 1 over x squared y squared equals x to the minus 2 y to the minus 2. Because we could write that 1 over x squared y squared as 1 over x squared times 1 over y squared. Then we can see where it matches up exactly. 1 over x squared is x to the minus 2 times 1 over y squared is y to the minus 2. Now, let's consider an example with numbers. Let's do 12 to the second power divided by 12 to the third power. This gives us 12 to the 2 minus 3, which is 12 to the minus 1. If we were to do this by expanding it, you would have 12 to the second power over 12 to the third power, which, when you cancel it out, would give you 1 over 12. This means that 12 to the minus 1 is the same thing as 1 over 12, and the rule does work. Therefore, if we have an example with other numbers, like x to the 48 over x to the 50, we could subtract and get x to the minus 2. If we do not like having a negative exponent, we can change it to 1 over the positive exponent, so 1 over x squared. Finally, let's look at what happens when you have a zero exponent. X to the fifth power divided by x to the fifth power gives us 5x's on the top and 5 on the bottom when expanded out. Since all of our x's cancel out as pairs on top and bottom, that means that we are left with 1. Because any number divided by itself is 1, x to the fifth over x to the fifth will also be 1. If we were to do the same thing using the quotient rule, we would get x to the 5 minus 5, which is x to the 0, because 5 minus 5 is 0. Since both of these stemmed from the same problem, we now have x to the 0 is equal to 1. So any number to the 0 power will give us a 1. Now, let's test out this rule to see if it works. X to the third y squared over x cubed y to the second power will give us 3x's on the top and 2 y's on the top. It'll also give us 3x's on the bottom and 2 y's on the bottom. Since the number of x's on top and bottom are the same, they cancel out. And since the number of y's on the top and bottom are the same, they will also cancel out when paired up. This means that we are left with 1. And if we do this using the rule, x to the 3 minus 3 is x to the 0, and y to the 2 minus 2 is also y to the 0. That means that x to the 0, y to the 0 equals 1. And if we separate this out into x to the 0 equals 1 and y to the 0 equals 1, we will in fact get 1 times 1 is 1. So this is true, this works. Now, let's try an example with numbers. Let's do 8 to the second power over 8 squared. 8 to the second power is 16, and of course 8 squared is also 16. 16 divided by 16 gives us 1. Now, let's try 8 to the 2 minus 2. Well, 2 minus 2 is 0, so you get 8 to the 0 power. Since these are both from 8 squared over 8 squared, we get 8 to the 0 equals 1, and our rule does check out. For the properties of exponents, if I was to give you an exponent expression, you would need to be able to simplify it or change it to another form. So you need to know, based off of the problem I give you, which exponent rule you're going to use and then apply it. You will need to apply it to both generic forms with our variables as well as numeric forms with numbers.